I've given you an introduction about telescope in the last two videos. If you haven't seen it, we'll post the link down below in the description. Please go and check out the first two videos about introduction of telescope and a bit more deep dive into what are the intricate things around telescopes, what are the issues that we generally face when we do research with telescopes in professional astrophysics and research. What happens, what are the limitations, what are the other ways. So I've given all the introduction over there. If you haven't seen it, the link is in the description below. So this video I will explain a little bit more about, let's go a little bit more deep dive, since we are more focused into the optics part. We'll have a separate series on astrophysics completely, where we'll deep dive into the physics between all these, the physics that goes in all these objects. For now, let's focus more on the astronomical instrumentation. What kind of instruments do we use? So I just wanted to explain to you all the cool kind of instruments that we work with. What are the different science that we can do with that instrument? What kind of research can be done with that instruments? And also, like, all the in the previous two videos, all the description and explanation that I've given till this point are all about optical telescopes. So if you look into the entire electromagnetic spectrum, optical wavelengths are a small bit of it. So I'll go into a little bit more into deep dive into infrared and ultraviolet and X-ray, gamma ray telescopes. I'll give you a quick overview of how infrared longer wavelengths like infrared or radio wave telescopes, how do they operate and what can we do about it. So I'll explain a little bit more around it. So yeah, in this video we'll go a little bit more into detail about all these different instruments, and we'll have a separate series on different concepts of astrophysics. So if you want to hear more about it, please do subscribe the channel. So yeah, let me get more into the, okay, so now for instrumentation. Now in the previous video I've explained that, okay, now that we know how a telescope functions, right? Now all we do in astrophysics is it's all about collecting the light. Now unlike any other science where you can go and change the state of a system, you can go and experiment, you can go change a certain state of a system to see how it reacts. The experiments are more done in a lab. Whereas in astrophysics, okay, there is a little bit of a laboratory astrophysics, but it's not exactly like we build a star in a lab, or we can, build a black hole in a lab. We don't have the technology yet to do that. So all we have is basically we can look up over there and try to figure out from the images. Based on the images, we try to figure out what's going on over there. So the only source of information that we have is photons and light. So we can't go and tweak up a star or nudge a star to see what happens if we do that. So we really have to sit, and if we want a star to be nudged, we have to sit back and wait for someone to go and nudge the star, not us. So jokes apart, so the thing is, all that matters to us is it's all about photons and how we collect the light and what do we do with this light. How much information can we collect from this light? So that's all we've got at hand, right? So what can we do with this? So I only have one source of information. What else? What can I do with it? So telescopes, all telescopes can do is it will just say collect that light, bring it, focus, and deliver it to you. Now, what do we do with this light comes the second half of it. So we basically, like, what can we do? Now, typically, like in the previous video, I have explained that one thing that you can do is put an eyepiece on it, put your eye, look at it. That's how it's done old school. Now, well, we now have something called as CCD or digital cameras. So now I can record the light. Now in the old days, what they used to do is they used to put a photographic plate at the image part of the telescope, on the image plane, that is after the instead of the eyepiece, they place a photographic plate, a chemical photographic plate that then reacts based on the light that is received from these stars. And then based on how these things react, they can figure out how bright this object is to a certain extent. But again, right, like this is even worse than doing science with, the analog, voltmeters or, current meters and stuff. So it's like these old school analog meters. So yeah, you can measure it, but there's still a lot of room for error. Now it's even worse than that, because right now I'm just going to look at it. Okay, my blob looks this big on my plate. The second blob of the other star looks this big. Okay, roughly this one should be twice as bright as the other one. It's basically by more or less, there's a lot more of guesswork and a lot of room for errors. But even with that, we have done a lot of science with it. Now, if you actually look at it, there are some, we are based here in Chennai. So if you are in Chennai, there is like, there used to be an observatory, the famous Madras Observatory in Nungambakkam. They shut it down during the British time. It was there in 1700s, during the time of Isaac Newton. Now in Madras Observatory, they used all these photographic plates, and they even like suspected like one star actually having a potential exoplanet. That was like one of the first ever exoplanet suspicion, but it wasn't an exoplanet, but was one of the first suspicion. So back then, like they could do it, but they could only suspect it. So I can't measure it, right? So now with a CCD, I can do it, right? So now this is where the age of astronomical instrumentation came out. So what can I do with these? So one is, well, imaging. Now the obvious two things. One is imaging, and the second one is, well, spectroscopy. These are the two famous ones that we do. Like most of our astronomical observation is either imaging or spectroscopy. Now what do I mean by spectroscopy? Well, we pass it through a prism, we disperse the light, we basically record the spectrum of the star, spectrum of the object rather than the image of the object, and we basically try to see the light over it. So now with imaging, well, I see the object, I need to measure how bright the object is. Based on how bright it is on different wavelengths, I can figure out I can figure out what type of object it is. So or like how it is on different bands. I can figure out how it is done. So typically for an imaging, I basically like can stick a camera over there and can do the science. And of course I need to add a filter to say, okay, what wavelengths we can do what. Now with a spectroscopy, typically I can put a prism or something called as a grating, diffraction grating. So the grating basically splits the light in a certain way, and then I can still see. And again, like there's spectral resolution and so on coming over there. Now what can I do like over here? So with spectroscopy and imaging, right, I want to go a little bit more deeper into the science behind it rather than boring you with all these different instrumentation things. So let's get on to the cool astronomy science behind it. So one science that I really like the most is research that I really like the most is about exoplanets. Now I think in the previous video I've explained about how can you detect exoplanets through direct imaging, like by looking at how the light dips. So I'll explain it again right now. So there are different ways in which we can identify exoplanets. So one is through what we call as occultation. So basically the planet goes in front of the star and we can figure it out. The next one is what we call as the radial velocity method. Next one is direct imaging. And the last one is not that famous. Like I've been a part of it, like that's one of the publications that I've been part of, but it's not a really famous technique because it's still a little bit difficult to achieve. It's something called as nulling interferometry. If I have time, I'll go a little bit more into interferometry and I'll explain this. So I just wanted to explain like in the instrumentation based on how we can do the science. So that's why I want to jump into how we work with exoplanets. So with occultation, what we do is essentially, again, going back to the thing, I basically place a camera in optical wavelengths, like a regular camera, and I basically record the light. I need to have a sensitive enough camera because I shouldn't just record the starlight, but I have to see even a minor variation in the starlight. So which means my room for error, I can't keep a photographic plate and say, it's twice as big as the other blob, so that means it should be a star. Like what the guys in Madras Observatory did back in 1800s. So I can't do that. So that's why we need a good enough camera, and not just a good enough camera. As I have explained in my previous video, also I need to account for all the errors that I might get because of Earth's atmosphere and so on. So what happens technically in occultation is, if I have a star, right, the surface of the star, and I have a planet going across the star, what happens is initially, if I just plot the brightness over time, the star's brightness will be stable, and at a point in time it dips, then it goes back up. It won't dip all the way to zero, but it usually dips a little bit. Okay, now with the level of how much it dipped and everything, I can figure out what type of planet it is. Now, in order to do this, I need to have a good enough camera that can sense this. So, and also these are like ultra short time frames, right? So, which means I need to have not just a sensitive camera, but like something called what we use. We call it EMCCDs. CCD, electron multiplying charge coupled devices. So EMCCDs are like these high frame rate cameras. Like you would have seen these YouTube videos where they pop a balloon and you see the balloon exploding and all these things. They are typically, those kind of fast cameras is what we need for most of these sciences. So EMCCD is one of them. So basically I need to measure it, but I need to measure it accurately and I need to measure it fast. That's why we need those kind of. The other one is the radial velocity method. So this is where we use spectroscopy. So now I explained about what is a spectroscopy, right? So instead of putting a camera directly, I place a small diffraction grating or something that splits up the light into spectrum for me, and then I can measure the light. Now let's say I have my spectrum, so let me just, I'm going to erase this entire part, let me just erase this entire part, I'll come to it later. So in spectroscopy, basically I have my starlight coming through my coming into my telescope, and essentially, let's say I have my secondary and so on. Now it all focuses and it goes through, right? Then I place a prism on the way. It can be a prism or a grating. I place something that can disperse my light. Then I get my spectrum over here. Now, if I place a camera at this point and record the entire spectrum, I can measure how bright it is at each of these points, right? So essentially what I have over here is at each point I have a different color, which means a different wavelength. So I can measure how bright it is in each wavelength at once. Now, typically out of this, we can plot something called as a spectrograph. Typically, I'll see a continuum emission, I might see some emission lines, some absorption lines, and so on. So what do I mean by emission and absorption lines is, if I have a light that hits, let's say you're looking at me right now, right? The light from the source over there hits me, and you can see this. Now, the photons that enters the camera in front of me, there are three types of processes that goes through. One is reflection, which is the major contribution, which is basically the light hits me, bounces off me, hits the camera, there is a CCD over there which is recording it, and now at the comfort of your home you're looking at it. Now that's reflection. The other one is scattering. That is my body, basically my body, based on a few other parameters, it can scatter the photons that comes out of me. That's the other one. The third one, that is where it is more important, is that these are basically photons, right? So the atoms in my body absorbs these photons, the electrons get excited, goes back down, it emits another photon. So this is basically either it can absorb, can go to an excited state and can stay there, or it can re-emit, or it can naturally, my body also, there's a fourth thing, my body also has a temperature, right? Because I'm at say 96 degrees Fahrenheit, so I don't have a fever or anything right now. So that means I emit infrared light, because I'm now I'm not a perfect black body, but I'm a black body, right? So I'm an emitter. So I emit light in infrared part of the spectrum. Not just me, even you are emitting light in infrared spectrum. So essentially there is also infrared photons that comes out of me, right? So now which means I have some emission part of me. Now this emission basically tells about me, right? Now if you look at me from an infrared perspective, you can say, does this guy have fever or not? Is this guy COVID positive? I mean, I hope not, but does this guy have fever or not? Or do I have hypothermia right now? If I'm really freezing right now because of the air conditioner here, okay, do I have that? Now you can see that through infrared light. Now instead of me as a person, it's the same thing that I can do it for a star, right? And based on the amount of light that I absorb and what wavelength of light that I absorb, I can identify what constitutes, what are the materials that I have in me, what are the elements that I have in me. So this we can do the same thing on a star or a planet. So that's what you typically see as a signature. So if you plot this, right, I'll have intensity, and if I plot it, I'm going to see emission and absorption line. So that's what we call as our spectrum. Okay. Now based on this spectrum, we can do a lot of wonders with it. One is, say, I can identify complex molecules in star forming regions. Say recently there has been publications where we have even found amino acids in star forming regions. So amino acids has a specific signature at certain wavelengths through which we can find, okay, this should be done by amino acids, right? These spectral signatures, the absorption and emission comes because of amino acids. Now why is it so cool? Well, hey, amino acids are the ones that forms proteins, and proteins are what makes you and me life. So which means if I found amino acids over there, life might be somewhere around there. Hopefully, we haven't found aliens yet, but a signature of life. So that's essentially why we look into spectrum. Now coming back to radial velocity method, right? Why do we really need the spectrum? So the point over here is, again, it's you might have heard about this effect called Doppler effect. That is, as an object approaches you and it emits, say you're listening to a car that is screeching horn and coming towards you, you're like, and it goes off, right? So as it approaches you, the frequency of the horn goes up, and as it goes away from you, the frequency of the horn goes down. Excuse me. So from this you can identify, is it approaching you or is it leaving you? Now this is what we call as redshift or blue shift. So redshift means technically it's like the frequency of the light goes more towards the longer wavelength, that is lower frequencies, which means the entire thing is shifting more towards red. That means the object is moving away from me. If it's blue shift, it's coming closer to me. Now if it does red and blue shift in a periodic way, that means it's doing some periodic motion. Excuse me. Okay. So if it does some periodic redshift and blue shift, it means that the object is doing something periodic. Now there is an interesting fact over here, that is, if I have a star and a planet. Now, till now, like we would have heard that, okay, the planet orbits the star. Well, in reality, that's not the case. The planet doesn't go around the star. The star and the planet, they orbit around a common center of gravity. So the planet doesn't go around the star, or the star also like typically goes, you can put it the other way around. So if I have a planet and a star, just because there is a planet over here, the star tends to wobble a bit because it has to go around this center of gravity. If I want to draw it bigger, let's say I have a bigger star and a bigger planet over here, and there's a center of gravity somewhere over here. So it's not just the planet that goes. Now typically the reason why we see that Earth goes around the sun is that this center of gravity is in most of the cases they are inside the parent object. Most of the cases it's inside the star. Now if you look at the Earth Moon system, the center of gravity is actually inside Earth. So that's why you see Moon going around Earth. So that means the star also tends to move around. So if I have a really, really faint planet, I can't really see it. Now what happens is, I know that the star is going to wobble a bit, right? Because it is also going around the center of gravity, which means the star is going to do a periodic motion, which means at times it is going to blue shift and at times it's going to red shift. So if I look into the spectrum of the star and I see like it's shifting, it's doing that red shift, blue shift on a periodic way, based on the period, I can figure out how big this planet is and how far the planet is. Now this is what we call as the radial velocity. Why radial velocity? Redshift and blue shift, I can only see it going on my plane of view. Now imagine you are on an airplane and there is not that high, but like say you're on top of a building and you see a car going below you. You won't have the same amount of Doppler effect as a person who's sitting on the road and who's on the line of sight. So that's why it's like you will see a stronger effect. Now because the star just wobbles, you need to have it on the line of sight. So this is where the spectroscopy comes into play. So I just wanted to give you like more from a use case perspective on why we use spectroscopy and imaging. Now there is a third one that we usually go for. Now even for imaging, now we also have direct imaging where I can take an image of a star and I can occult I can basically take an image of the star and I can occult, like I basically place a fake eclipse in front of the star. So it's basically like, let's say I have my light over there and there's something faint right next to it, right? If you're looking at it, you typically put your thumb or your hand in front of you just so that you can see the star right next to it. So this other part is what so the other part is what we generally so this one is what we use for imaging actually. So we create a fake block for the star. So if I have the star, I create a fake block around it, and if I shoot an image, I'm going to see the planet. So yeah, so this will definitely continue on the next video. I'll go a bit more detail into the science behind it. So hopefully I've explained, you understood, like it's not just the telescope but the instrument behind it that plays all the role with it. And it's not always like a simple prism or a spectrometer. We also have, we like to take all these images, we also have optical fibers which collects lights from different parts of the image plane, and then we do some science with it. There are also now cooler new things called integrated optics. I used to work with it. It's where, like, if I have a huge, like typically if you look into if you go to an observatory and check out their spectrographs or check out their imaging setup or their interferometry setup, be a massive optical bench with a bunch of quarter wave plates, lenses, mirrors, everything standing here and there. But now what integrated optics are is basically you take all of this and put it in a chip to the size of my thumb, and it does the same thing. So which I'll explain further in the next video. So thanks for watching, and please subscribe and please check the links in the description below for the first 2 videos. Thank you.